there any questions before we get started? Very good.
I have a question. No, I'm just kidding. I don't have a question.
Is that the last
What is that?
Ken will be here shortly.
one? Is that the last one?
Where is it?
Last one.
Oh. Okay. So we are talking about asymptotic expansion of integrals. Sommerfeld integral in particular. These are very complicated integrals, and they by themselves do not offer much physical insight, except that they are pavement expansion of sources propagating through layered medium. But if you perform asymptotic expansions on them, you can gain further insight. And I think we did the case of a vertical magnetic dipole last time. And today I'd like to do the case of a vertical electric dipole. And there's some new insight to be gained for the vertical electric dipole case. And so if you have a vertical electric dipole, the electric field will look something like this. Okay? The magnetic field will look something like this. Hv. Okay, H is primarily Hv. So this produces primarily a Tm wave. Okay, there's the insight that we can gain even before we solve the problem. So if it's the Tm wave, then it must be expressible in terms of Ez. Okay, Ez is not equal to 0, Hz equal to 0. That is the peculiarity of this one. Ez not equal to 0, Hz equal to 0. And then we in fact have solved this problem before, and our E1z in fact looks something like this. In region 1, K rho cube over K1z, H01, K rho rho, and then multiplied by e to the I K1z z, okay, plus a reflected wave term, R12 Tm, because this is a Tm wave, e to the I K1z z plus 2d1. Okay, this 2d1 is judiciously selected so that these two phases are equal to each other at z equals minus d1, and this represents the reflection coefficient. And the direct field term is quite simple. I'm sure that you know how to get it back to the analytic solution for the direct term. But then the reflected term can never be evaluated in closed form because of this complicated reflection coefficient. This is a complicated function of K rho. There's no way you can have this evaluated in closed form. So we can use asymptotic expansion technique to evaluate the reflected field term, which is this times a constant times this Sommerfeld integral. H01 K rho rho, and then times this very complicated reflection coefficient. Okay. The key to finding the approximation of this Sommerfeld integral is actually the ability to identify critical points in the integrand, to find where the critical points are. In order to figure out where the critical points are, it will be good to sketch the steepest descent path, the branch cuts and the branch points for this integrand. R12 Tm as you recall, is equal to this one. Epsilon 1 K2Z. Okay? So, the integrand is a function of K1Z and K2Z. And K1Z is K1 squared minus K rho squared. The integration variable is K rho squared. K2Z is K2 squared minus K rho squared. So you can see that there are two branch points for the integrand already. And of course, you know that H01 K rho has this exponential phase function behavior. And together with that, you can work out the steepest descent path. Okay, and so it will be necessary for us to work out the steepest descent path. And let's look at how it looks like in the complex plane. This is K rho prime, K rho double prime. This just means real and imaginary part. There are two branch points, K1 and K2. Okay, and there should be one at minus K1 and minus K2 also, but let's not worry about this one at this point. Okay, K2 is over here. And we can sketch the branch cuts that go through these branch points. We choose the Sommerfeld branch cut, which is the imaginary K1Z equal to 0 branch cut. The one that goes through K1 will look something like a rectangular hyperbola. Okay, so in the small loss case, it looks something like this, and the loss gets bigger, it will look more like a circle. But in the case of vanishingly small loss, it looks something like this, and in the case of no loss, it will have the imaginary and the real axis very tight. Okay, this is a small loss case. And we like to introduce some loss so that it's easier to draw the branch cuts. Otherwise, it's kind of difficult to draw them. Because otherwise, they will have the real and the imaginary axis too tightly. And of course, this is the branch cut associated with this one, and this is the Sommerfeld branch cut. Imaginary K2Z equal to 0. The other one is imaginary K1Z equal to 0. The corresponding branch cuts going there, and let's not worry too much about those on the other quadrant. Okay. So these branch cuts are important because they are the gateway to the top and the bottom Riemann sheet. Okay, in the top Riemann sheet, it will be imaginary K1Z larger than 0, and in the bottom Riemann sheet, there will be imaginary K1Z less than 0, and similarly for K2Z. Okay, so these are the critical singularities of the integrand. And of course, the next thing you should do is to combine this phase function with this function and look for the stationary phase point, or the steepest descent point, or the setup point. It turns out that there's a setup point somewhere around here, given by K1 sine theta I. Theta I is what I already worked out before. It is the location of the image point. If this is the source point, there would be image point, and if there's a geometrical optics theory that you can draw, theta I is this angle. Okay, this is V1, D1, and this is V1 plus Z. Okay? And that is your theta I, and will not work out this stationary phase point again for you. I'm sure that you know how to work this out. Okay? This is the location of and of course, if you were to work out the steepest descent path, you work out the steepest descent path by equating this phase function to be equal to I H T0 minus I be lambda here, lambda s squared. So not lambda s, but just s squared. Okay. You work out this equation, and this is the equation where the phase does not change. This is called a constant phase path. If you keep s to be real, and you can work out a constant phase path that passes through the center point, it will look something like this. And here it actually has to cross a branch cut 2 times. And then cross the branch cut 2 times again and emerges. So this is the steepest descent path that passes through the saddle point. This is the saddle point. Okay, and our integration path for this original integral is a Sommerfeld integration path. And it looks something like this. We call it SIP. Okay, the others call it Sommerfeld branch cuts. So we need to deform from the SIP, the Sommerfeld integration path, to the steepest descent path. Maybe we can call this S1, the steepest descent path that passes through the saddle point. And of course, the deformation is not possible. So what we need to do is actually to identify the steepest descent path that passes through the branch point K2. And that one looks something like this. The steepest descent path does not depend on K2z. This function from which you find the steepest descent path does not depend on K2z. So they have the same path on the top and the bottom Riemann sheet of K2z branch cut. Okay. So after you have added this steepest descent path, let's call this S2, then we can deform SIP, which is along this path, to S1 through this, and here it crosses the branch cut 2 times. First time it crosses it, it will go to the bottom Riemann sheet of K1z branch cut. The second time it crosses the other branch cut, it will go to the bottom sheet of K2z branch cut. So at this point, this is the bottommost Riemann sheet. Okay, you're at the bottommost Riemann sheet when you're there. That small little path there, because you have to cross the branch cut 2 times. Can everybody see that? And then as you cross the branch cut 1 time and 2 times, you emerge from the bottom Riemann sheet again to the top Riemann sheet. So this is actually the topmost Riemann sheet. Okay. And then you cross a branch cut 1 time, you get to the bottom Riemann sheet of this. And this is the bottom Riemann sheet of K2z, the imaginary K2z branch cut. And then you can connect, and then finally, if you were to choose to integrate like this, then you can come back again from infinity and then integrate like this. You have the topmost Riemann sheet, and then you can connect and complete the path, complete the path deformation. And you say that the original Sommerfeld integration path is the same as integrating along this path. Okay? And there is a nuance point that I haven't talked about quite yet, because this is the TM case. TM case allows for the possibility of this to have a pole. The denominator could go to 0. That is a very subtle point. So if you solve this equation, equal to 0, it gives you the pole location. And then if you were to solve for the zeros, K1z minus F1K2z equal to 0. Okay, it gives you the 0 of the reflection coefficient. Does anybody remember what physically this means? This is the Brewster angle. Okay, this is the Brewster angle 0. And the other one is called the Sommerfeld pole. So everything got named after Sommerfeld. Okay? And the Sommerfeld pole and the Brewster angle 0 are actually at the same location, because in order to solve this equation, you have to take this to the right hand side and square the two equations. When you square the equations, the two equations are the same. Okay? You square the two equations, and then if you were to solve them, then you have epsilon 2 squared k1 squared minus k rho squared equals to epsilon 1 squared k2 squared minus k rho squared. Both equations, once you square them, give rise to this equation. Okay? And if you were to solve this equation, it gives you k rho squared epsilon 1 squared minus epsilon 2 squared is equal to epsilon 1 squared k2 squared minus epsilon 2 squared k1 squared. But let's assume that the medium is non-magnetic, so that this can be written as epsilon 1, let's pull out omega squared mu 2. Mu, let's assume that the medium is non-magnetic, so that mu is the same for both cases. So it will be epsilon 1 squared, epsilon 2 minus epsilon 2 squared, epsilon 1. Agree? If mu is the same for both of them, this is what I get. Agree? So if you solve this further, you find that k rho, well, if I simplify this further, this is omega squared mu epsilon 1, epsilon 2, epsilon 1 minus epsilon 2. This I simplify the right hand side further. But then there's an epsilon 1 minus epsilon 2 in here, because this is the completion of the square, right? A squared minus b squared. So finally I get k rho squared is equal to omega squared mu epsilon 1 epsilon 2 divided by epsilon 1 plus epsilon 2. Okay? And this gives you the familiar formula that you might have encountered before. K rho is equal to K1, as you say, is K1 epsilon 2 over epsilon 1 plus epsilon 2. Does this formula ring a bell for some of you? What is that formula? That's the Brewster angle formula that you learn in some undergraduate course, right? And it happens to be always less than 1, because this factor is always less than 1. So this is the Brewster angle. Okay, this factor is always less than 1. You can look for the Brewster angle from this thing. And that is the Brewster angle location. But the same equation for the pole also gives you the same equation. Okay, so the Sommerfeld pole is also equal or given by this formula. Okay, and this is a dilemma. How come the pole and the zeros are at the same location? So how do we justify this? How do we get ourselves out of this dilemma that the pole and the zeros are at the same location? They must be on different Riemann sheets, right? If you go back and study this equation again, if epsilon 1 and epsilon 2 are both positive numbers, okay, this must be happening on the Riemann sheet where k1z and k2z are both real. Okay? And if epsilon 1 and epsilon 2 are both positive numbers, the pole must be happening on the Riemann sheet where one k1z or k2z is opposite in sign to each other. Okay? And it turns out that if you do things properly, if there is in fact a pole, let's just hypothesize that the pole is here. Okay? Let's just hypothesize that it's here. Just assume that the pole is there. The 0 is also at the same location. But the 0 is at the location where the imaginary part, of the K1z and K2z must be the same. Okay, let's assume that epsilon 1 and epsilon 2 are pure real. Okay, so this could only happen at the bottommost Riemann sheet or the topmost Riemann sheet, and let me explain to you why. Okay, at the topmost Riemann sheet of both of these two, imaginary K1z are both positive. At the bottommost Riemann sheet of these 4 Riemann sheets that we have, imaginary K1z and K2z are both negative. Okay, those are the two occasions where these two can cancel each other, right? They can cancel each other. They cannot cancel each other at the second or the third Riemann sheet. There's the topmost, there's the bottommost. Okay, but there is some other Riemann sheets in between, and those two Riemann sheets, the two numerators cannot cancel each other. So the Brewster angle 0 exists only at the bottommost Riemann sheet and topmost Riemann sheet. And by the same argument, okay, at the second, if I have this topmost, and then there are 4 Riemann sheets, right? If you go through there are 4 Riemann sheets, and then it's the bottommost. The Brewster angle is associated with this topmost and the bottommost. Okay, in between you can have the poles. The poles are there. Okay, so the pole is also at the same location, but at the second or the third Riemann sheet. Can everybody see that? So when you detour from this path to that path, do you encounter the pole or you don't? Do you encounter the pole? Should we pick up the pole contribution? Is a pole at the bottommost? Is a pole at the bottommost, the second or the third or the first? The 0 is the bottommost. So we never encounter the pole when we detour. When we detour inward, okay, we never encounter the pole because the pole is at the second or the third Riemann sheet. Okay, some of you did make a mistake the first time you solved this problem. You thought the pole was contributing. Okay, included the contribution of the pole, but later he corrected himself, coming to the realization that the pole actually does not contribute. So this pole was called the Sommerfeld pole. And of course there are a lot of histories about this pole. You can read up about the history of the Sommerfeld pole. Okay, it never really contributes to the contour deformation. But you do observe the Brewster angle. That is, there's some angle when you get extremely close to the zeros of the Brewster angle. It's hard to draw this diagram. If you draw it in the limiting loss case, you can go through the same argument and argue that it's only on the bottommost Riemann sheet that you see the Brewster angle. At the other sheets, you do see the pole, but the pole is never picked up by this. Okay? So this is the famous Sommerfeld pole. It never really contributes. Okay? And then there are lots of argument in the literature saying that perhaps it does contribute sometimes. Saying that if you introduce some laws, maybe the branch cut will distort themselves somehow, and then we have to include the pole location. Okay? The pole location in that case is called the Zanek surface wave pole. And some people think that it should contribute, but in my opinion, it does not, because it's on the wrong Riemann sheet. The Zanek surface wave pole never really contributes to the Sommerfeld integral as it detour the contour from the rear axis to those contour. Yes.
So if the when losses introduced, those branch cuts move outward?
Right, they
There's no
become
chance.
more like this. If I introduce some loss, maybe it will look more like a rectangular hyperbola. And I might have something like this. And then there will be a Brewster angle 0 that maybe manifests itself somewhere here. Okay. The Brewster angle still has to be at the bottommost Riemann sheet of all these things. Okay. Actually, things are quite complicated here. Okay, because you are at the bottommost Riemann sheet and some of those things, and you can convince yourself that if you were to detour, you only pick up the Brewster angle contribution, never really the pole. Okay? The pole is always at the wrong location, wrong Riemann sheet, that you don't pick them up. And actually, I don't know if you recall the mapping I had before to you that that this shore of the branch cut actually corresponds to real K1Z is less than 0, and the other shore of the branch cut corresponds to real K1Z is larger than 0. Because this maps to the real axis, and then if you go to those arguments, and this has two shores, and then there will be real K2Z less than 0, and then real K2Z larger than 0. And you go to those arguments using both the real and imaginary part of those. The pole never really contributes. The Zanic surface wave pole really never contributes. It can affect the wave. It can affect the wave because it's a pole nearby and it can influence the data point contribution, but it never really contributes as a special surface wave. Okay? So there are lots of controversy in the literature about that, but my opinion is that it doesn't really contribute. Okay? So those are the critical points. As you can see, the pole never really contributes. The center point is a critical point. So as lambda goes to infinity, or if Rm goes to infinity, it's those critical points that contribute the most. Is this point over here. This point is like the top of the hill. Think of this as a steepest descent path. Everything else is small compared to this peak, or this point here, which is top of the hill. You're climbing the hill, and this is the top of the hill. And this is like, also if you climb this hill, this is even a bigger hill to climb to, right? So this is actually a very important point. As lambda goes to infinity, this integrand will peak here. It will peak somewhere here. So this, as I told you before, if there's a critical point contribution, you look at the phase function. You look at the phase function. At that point over here, this phase function will become having a spherical wave phase function. And then, of course, it has a denominator due to the integration of other things. Those are harder to prove, but then we prove by stationary phase point method that this thing is actually 1 over Ri dependent. And then this one is a branch point contribution. It's harder to evaluate. You have to go through a lot of gymnastics in order to evaluate the branch point contribution. But in your homework, I asked you to do the second problem. Don't have to go through the gymnastics of doing all the detail. But just tell me what the phase of the wave is. That's the most important physics of the wave. So you ask yourself, this is the integrand. The integrand is going to peak here. And how does the integrand look like at the top of the hill? You just evaluate this integrand, okay, at this point over here. So you can immediately see that this phase function is going to be evaluated at k rho equals k2. Okay? So you're going to evaluate this at k rho equals k2. And this would become e to the I k2 rho plus I or it becomes, if you put this in, it becomes k2 squared minus k1 squared z plus 2d1 with a minus sign here. Okay, it's on the top Riemann sheet of k1z, so this comes up to be the right sign. So if you evaluate this point here, this is the phase. This phase denotes what I call the lateral surface wave. Lateral surface wave is a wave, so there are a few ways that the wave can reach the observer. One is a direct wave, one is this reflected wave, which is this term over here. The direct wave term is this term, which we never did anything about. But there's also another possibility that the field can reach the observer via the surface wave. So there's some evanescent wave that the source generates, excites a surface wave that propagates with this phase velocity, okay, and then reaching the observer via an evanescent wave decay again. So if you look at the evanescent wave decay, the decay is first d1, and then there's another decay d1, and this part is z. Okay? So the total decay is z plus 2d1. There's an evanescent wave decay. So this wave reaches the observer in this manner. And how does this wave come about? This wave comes about because of the presence of the spherical wave in region 2. Your homework, you're asked to find the spherical wave in region 2. Okay? So what happens is that if you put a source here, it's going to generate a spherical wave here. Let me see. If it's going to generate a spherical wave here, the wave has to be longer here. And then over here, it will generate a spherical wave with a shorter wavelength. Okay, this spherical wave has a shorter wavelength. As this spherical wave propagates with a shorter wavelength in region 2, it's going to generate evanescent wave in region 1. Okay? And this can be thought of as due to the spherical wave in region 2. That's why we have this wave. And it turns out that this wave decays with 1 over rho squared decay. This 1 over rho squared decay is harder to arrive at. You have to do all the details of the mathematics to get the decay rate. And this is how the wave looks like. So this is the lateral surface wave. And sometimes it's also called a head wave in acoustics. If you're in acoustics, this dinero can come about. This dinero can come about. You can have a fast medium, a slow medium, okay? But in electromagnetics, this is fast, this is slow. Optically more dense, optically less dense. But in acoustics, this could happen. So when you have this thing, so what happens then is that the wave that propagates with the spherical wave in region 2 actually has a longer wavelength instead of a shorter wavelength. The one that propagates in medium 1 has a shorter wavelength. Okay? Because it's fast and slow. So this corresponds to a wave that can reach the observer without being evanescent in region 1, because this is e to the I k2 rho kind of behavior, reaching the observer in this manner. Okay? So here are 3 ways that a wave can reach the observer in an acoustic medium. It also occurs in electromagnetics. This is optically less dense, this is optically more dense, but in acoustics it's more frequent. Okay, it turns out that this is called a head wave because you can arrive first. This is slow, but this one can be fast. Because this distance, the sound wave can go very fast, especially on the solid ground. In the solid ground, the velocity of sound is roughly equal to velocity of sound is something like the Bach modulus over the density, right? If this is very solid material, this can be this Bach modulus can be very large, And then if the density is not very high, the velocity of sound in a solid medium can be faster than velocity of sound in air. And it turns out that the sound wave can reach a person faster by going through the ground. Okay, so that's why you see in very old movies. I don't know, you guys are too young to look at old movies. Don't know the hero John Wayne. Do you know who John Wayne is? You know him, right?
Who?
John Wayne, you know?
I don't know.
Oh, okay. In his movie, he was a very heroic cowboy, right? And then he was always fighting the Indians. And when he wanted to listen to how the Indians, or when and where they're coming from, he would put his head to the ground and listen for the head wave, because he would hear the sound of the hooves. And those sounds travel faster through the ground. Okay, so those cowboys knew about this long ago. Okay, yes?
Does the contribution of the two different waves, does this have anything to do with like ghost tension shift?
Yes, ghost tension shift is a different thing. Because this angle is actually the critical angle. Okay. This angle is actually the critical angle. If you go through the analysis, that angle is the critical angle. And this is the angle that, if the wave comes in, it will become horizontal in the other medium. Greater than the critical angle, okay, it will be reflected. Larger than the critical angle, it will be reflected, and greater than the, smaller than the critical angle, it will be transmitted. But this is the angle that the transmitted wave will be horizontal. Okay, so it has something to do with the ghost tension shift, but not completely. Because this phase shift, ghost tension shift is something else, but this phase shift is entirely due to the fact that there's a spherical wave propagating in region 2. Ghost tension shift is not that. Ghost tension shift is a phase shift due to the